In the last lecture, we have seen definition of DFT, need of DFT. We compared it with DTFT. You know that DFT is a sampled version of DTFT, and we also know that DFT is calculated for finite length sequences. Today we'll do some calculations. We'll solve some examples. So we take first example to calculate 4-point DFT of x of n sequence is given as x of n is equal to 0, 1, 2, 3. So 4-point sequence is there. N is equal to 4. We have asked to find out 4-point DFT of the sequence. So let us write the definition first. X of k is equal to summation n varying from 0 to n minus 1 x of n e raised to minus j 2 pi by n kn, where k is varying from 0 to n minus 1. Okay. Now x of k, and k is varying from 0 to n minus 1. So we'll modify this definition for n is equal to 4. N is equal to 4. We have x of k is equal to the same definition. We are replacing n minus 1 by 3, 4 minus 1. X of n e raised to minus j 2 pi by n. N is equal to 4, means 2 pi by 4. That will be equal to pi by 2 kn, where k is varying from 0 to 3. So we have to calculate 4 values. K is equal to 0, x of 0, k is equal to 1, x of 1, k is equal to 2, x of 2 and x of 3. So first we'll go for k is equal to 0. So x of 0, n varying from 0 to 3, x of n e raised to minus j pi by 2, k is equal to 0 into n. So this factor e raised to, the whole thing is becoming 0, e raised to 0 is equal to 1. So this will become summation n varying from 0 to 3 x of n. So this means that sum of all the points x of 0 plus x of 1 plus x of 2 plus x of 3. So all these points 0 plus 1 plus 2 plus 3 is equal to 6. So the first point of the DFT x of 0 is equal to 6. Likewise, we'll calculate the second point for k is equal to 1. So x of 1 we'll say. Now we are going to use this definition. N varying from 0 to 3, x of n e raised to minus j pi by 2, k is equal to 1 into n. So we'll spread this. N is equal to 0 to 3. So x of 0, put n is equal to 0 first, e raised to minus j pi by 2 into 0 plus, now put n is equal to 1. So x of 1 e raised to minus j pi by 2 1 into n plus x of 2 e raised to minus j pi by 2, sorry, I've written n here by mistake, 2 plus the last sample 3, x of 3 e raised to minus j pi by 2 into the value of n is equal to 3. Okay. So we'll put the samples x of 0, 1, 2 and 3 here. X of 0 is 0 multiplied by e raised to 0. Okay. So that will be 0 into 1, that will be 0 plus x of 1, sample is 1, e raised to, now we have to calculate e raised to minus j pi by 2, e raised to j theta, we can write in terms of cos and sine. So e raised to j theta is equal to cos theta minus j sine theta. So here we'll write this cos pi by 2 minus j sine pi by 2 like this, plus x of 2, I'll write here x of 2 is 2 multiplied by e raised to, now j pi, e raised to minus j pi, you can write it like this, cos of pi minus j sine pi, plus the last sample x of 3 is equal to 3 into e raised to j 3 pi by 2. So you can write it as cos 3 pi by 2 minus j sine 3 pi by 2. Now after solving all this, I am getting the answer as minus 2 plus 2j as the second sample after solving this. Likewise, we need to solve x of 2 for k is equal to 2 and x of 3 for k is equal to 3. So we will get all the 4 points. So I will write all the 4 points here. I am not calculating the other values. Now you got the idea how to solve this. So x of k, the 4 samples of DFT are the first sample was 6 minus 2 plus 2j minus 2 and minus 2 minus 2j. So this is x of 0, x of 1, x of 2 and x of 3, the 4-point DFT of the signal. Now if you observe in this example, we have to calculate several times that e raised to j theta factor. So and it is very hectic to write again and again these things. So there is just a little bit modification in the definition. You know that the definition is like this. For x of k, we have summation n varying from 0 to n minus 1, x of n e raised to minus j 2 pi by n kn, where k is varying from 0 to n minus 1. Now we'll put a factor called as twiddle factor. This omega n is equal to e raised to minus j 2 pi by n. Okay, we'll put this in this definition, so it will become x of k n 0 to n minus 1 x of n. The rest of the things are same, we are just replacing this. Now raised to k n, where k is varying from 0 to n minus 1. So this will be the modified definition. Meaning is same, just we are representing this factor as a new factor called as twiddle factor. So it is very beneficial to write this definition in this short form, and it is also helpful to us in the further calculation, how to reduce the further calculations, that we'll see in the next lecture. And now we'll see again the definition of inverse DTFT. We have the same factor here but with the plus sign. So 1 by n, the k is varying from 0 to n minus 1. It is calculated from x of k e raised to j 2 pi by n kn, where n is varying from 0 to n minus 1. Now we'll replace this factor. Minus sign is not there, so this becomes an inverse. So x of n, new definition will become 1 by n summation k varying from 0 to n minus 1. This x of k will be the same, e raised to, now this factor raised to minus 1 multiplied by kn. n varying from 0 to n minus 1. So this is a new definition for inverse DFT. So these definitions are in the short form. We'll see more examples. Suppose a unit impulse signal x of n is given as del of n. You know that the del of n is present at n is equal to 0. Its amplitude is 1. So this signal is del of n. You want to find out DFT of it. So write the definition x of k summation n varying from 0 to n minus 1 x of n. I'll write del of n e raised to, or we'll write the modified definition, raised to kn, where k is varying from 0 to n minus 1. Now you know that del of n is present at n is equal to 0. So n is equal to 0 is only the unique value we are going to get here. There are no other values, so no need of summation. So this will become its amplitude 1 multiplied by this factor raised to, now kn, n is equal to 0. So k into 0. So the answer will become 1 for k varying from 0 to n minus 1. Okay. Now we'll see a shifted impulse signal. X of n is equal to del of n minus some shift n0. So this signal will look like this. Del of n minus n0. So it is present at n is equal to some n0 value. So only one value is present at n0 and its amplitude is 1. So similarly we'll solve this. X of k is equal to n starting from 0 to n minus 1. Now this del of n minus n0, this factor, middle factor, where k is varying from 0 to n minus 1. So you are going to get the value only at n is equal to n0. So its amplitude is 1 multiplied by omega n k, n is equal to n0. So this is the answer for k 0 to n minus 1. So elaborately we will write this answer as, put the value of k is equal to 0. Okay, first value 0 n0. Okay, so this value will become 1 n, k is equal to 1 n0. So n0. Next k is equal to 2 n0, and so on. The last value of k will be n minus 1 n0. So such a n values, capital N values of the DFT will exist for this signal. So now we'll see a different example. X of n, a signal x of n is equal to a raised to n for 0 to n. The range of n is given as this 0, otherwise. So it is a finite duration sequence which exists between 0 to n minus 1, and we want to calculate endpoint DFT. So first we'll write out the definition. X of k, n varying from 0 to n minus 1, x of n. So I'll write the signal itself, and the signal is existing from 0 to n minus 1. So you can write it like this: e raised to minus j 2 pi by n kn, where k is varying from 0 to n minus 1. Okay. Now we'll take this n common, as we need to apply one formula. I'll write here. N is equal to 0 to n minus 1 a e raised to minus j 2 pi by n k raised to n. Now here we are going to apply a formula, limited range summation of few points like this. Suppose n is varying from 0 to m, so this is a limited range alpha raised to n. So this is like this same. So you can write it as 1 minus alpha raised to the upper limit plus 1 divided by 1 minus alpha. So you can apply this formula directly here. So we'll get alpha, a, e raised to minus j 2 pi by n k. Okay, this thing raised to the upper limit plus 1. So here raised to n 1 minus a e raised to minus j 2 pi by n k. Now this n we'll write like this: 1 minus a raised to n e raised to minus j 2 pi by n k into n. So this n will get cancelled and we'll get here e raised to minus j 2 pi k divided by 1 minus a e raised to minus 2 pi by n k. Now this factor, this e raised to minus j 2 pi by 2 pi k. So this thing we can calculate the value by putting the definition of cos and sine. Cos theta minus j sine theta. So cos 2 pi k minus j sine 2 pi k, and k are the integer numbers all. So this value can become 2 pi, 4 pi, 6 pi, 8 pi, like this. So cos multiples of 2 pi, these values are 1, and sine 2 pi, sine 4 pi, sine 6 pi, sine 8 pi, these values are 0. So that this term will become 1, and the ultimate answer you can write like this: 1 minus raised to n 1 minus a e raised to minus j 2 pi by n k. So this k again is varying from 0 to n minus 1. So range of k, writing range of k is very important in this example. So this is the DFT of the sequence. Now we'll see one more example. X of n is given as cos 2 pi by n Rn. The range of R is from 0 to n minus 1. N is also from 0 to n minus 1. So you can calculate n point DFT for this example. X of k, writing the definition, n varying from 0 to n minus 1. The signal x of n, instead of x of n I am writing the signal here: 2 pi by n Rn into e raised to minus j 2 pi by n kn, where k is varying from 0 to n minus 1. Now we'll write this cos in terms of phasors: e raised to j theta plus e raised to minus j theta divided by 2. So x of k, that will become, now this part, just I'm replacing this part by the phasors: e raised to j 2 pi by n Rn plus e raised to minus j 2 pi by n Rn, I'll rub this, divided by 2 into e raised to minus j 2 pi by n kn. Now we'll take this 1 by 2 factor outside of the summation, multiply this factor by this factor plus this factor by this factor. Okay, so e raised to a, e raised to b, e raised to a plus b, that will happen here. So half into summation n 0 to n minus 1. So this first, we'll see what things are common here. 2 pi by n, r minus k n plus, in this factor what things are common? Minus j, 2 pi by n r plus k n. Okay. Now here in this factor, e raised to j somewhat theta. So this value, if this value becomes 0, so this whole factor will become 1 and we are summing this 1 for n times. So this sum will become n if r minus k is equal to 0. If r minus k is not equal to 0, then this term will become 0. So we will have a unique answer 1 if this term is 0. So for this we need k is equal to r. Okay, for this term. So that answer, summation of e raised to this term 0, 1. So we are summing 1 for n is equal to 0 to n minus 1. So that will become n. Okay. So that is a different part. So this will become summation of this. If k is equal to r, then this part will become n. The value is possible only for k is equal to r. So only one value, so we will represent like this, del of k minus r. Okay. Plus, now here you can see r plus k. So this value, if this value is 0, this whole factor will become e raised to 0, that is equal to 1. Otherwise, for the rest of the values, that factor will become 0, and 0 summed for how many times it will become 0. So we want this here, k is equal to minus r, and you know that this is periodic with period capital N. So we can also write it as n minus r. Okay. So you can put this value, when this value will become 1, sum for 0 to n minus 1. So that will become n. And it is only present for when k is equal to minus r. So here k plus r minus n. Okay, so that will be the answer, DFT. So you can also write it as, now these two things are simultaneously, these two things are not one, so only one thing will be present. So its amplitude is 1 n by 2 for this factor, n by 2 when k is equal to r. Okay. Again, if this is 0, this is going to be there. So this is n by 2 for k is equal to n minus r, and otherwise it is 0. So like this, we have solved a number of examples for DFT. In the next lecture, we will see Tweedle factor.